Welcome to Brain Vision.
So let's draw a free body diagram. So we can draw the wheel. We can draw the wheel, and this would be the radius of the wheel. Going straight down would, of course, be mg, or rather, let's say capital MG. And then we can say that the wheel is rotating to the right. This would be your y, this would be your x-axis, and we can say going straight up would be the force normal. And now for part A, it's asking which direction is the force of friction acting. So the frictional force actually accelerates the center of the mass of the wheel. So we can say if the wheel is spinning and slipping clockwise in the diagram, which we have drawn, we can say that the surface of the wheel that touches the ground is moving to the left. So we can say surface of wheel touching ground is moving to the left. And if it is moving to the left, friction always acts in the direction opposite of the motion. So here, we could say that the frictional force is to the right. So this is how we would represent that. And at this point, this would be your answer for part A. For part B, we're just simply going to apply Newton's second law. So we can say that the sum of forces in the y direction would equal force normal minus mg. This would equal 0. So we can say force normal equals the weight of the wheel. Sum of forces in the x direction would equal force of friction. This would equal the mass of the wheel times the acceleration of the wheel. Therefore, the acceleration would simply equal the force of friction divided by the mass of the wheel, which would equal the coefficient of kinetic friction times force normal divided by m, and this would equal mu kg. We can say that then the sum of torques, or rather the net torque, is going to be equal to the negative force of friction times the radius of the wheel. This is equaling the moment of inertia of the wheel times the angular acceleration. Therefore, the angular acceleration would equal the negative force of friction times the radius of the wheel divided by 1/2 mr squared. And we can simplify. So this would be equal to negative 2 mg divided by mr. And let's cancel out the m's. And the angular acceleration is found to be negative 2 mu kg over r. So essentially, we could say that, oh, my apologies, this would be A. And at this point, we know that both the acceleration and the angular acceleration are constant. So we can use kinematics, and we can say that velocity final equals velocity initial plus at. This would equal mu kgt because the initial velocity is 0. Therefore, the final angular velocity would equal the initial angular velocity plus the angular acceleration times t. This would equal the initial angular velocity minus 2 mu kg t over the radius of the wheel. Note that the velocity starts at 0 and increases. So we can say that the angular velocity would equal v over r. And at some specific time t, the velocity and the angular velocity will be equal to omega equals v over r here. And the ball will roll without slipping. So here, let's solve for the value of t and say that omega equals v over r. And we can say that omega initial minus 2 mu k g, some value t, divided by r will equal mu k g over r. Solving for t, we get that t is going to equal the omega initial times r divided by 3 mu k g. And this is the time where omega equals v over r, ball, or we can say rather, wheel does not slip. So this would be our answer for part B. That's the answer for part B. And then for part C, once the ball starts rolling without slipping, there is no more frictional sliding force. And so the velocity will remain constant. We can say that velocity final will then be equal to the coefficient of kinetic friction times g times t, what we found in part B. And then we're simply substituting in for t. So mu kg multiplied by omega initial r divided by 3 mu kg. And we find that the final velocity would simply be equal to r, the radius of the wheel, times the initial angular velocity divided by 3. That would be our answer for part C. That is the end of the solution. Thank you for watching.